Hello, I'm pleased to meet you again to start another lesson. This time it will be about the sketching of graphs. The meaning exactly of the sketching of graph is not to exactly precisely draw the graph of function, but just to adjust oneself or to get acquainted with the main properties of the graph. Whether it has a maximum, whether it has asymptotes, whether it has a global extrema or a local extrema, etc. It's a kind of primitive, or let us say simple graphing of the functions, crude ones. Now, usually what is strange is that I'm always confronted by the question from my students saying that when I give them any question of calculus, they usually tell me, sir, should we graph the function? And I tell them, no, you don't have to. But even if you do need or you do want to graph the function, then it's no big deal. It's very easy to draw graphs of function. You don't need to resort to calculators, graphing calculators to do them, or to expensive software like the MATLAB or Mathematica or whatever. No, it's easy to get acquainted with the simple properties of such graphs. They all look similar and they all do the same. You do the same steps in order to graph any function. So in this lesson, we shall be explaining the steps in which you follow in order to draw the graph of any function which you wish to. Now, in this lesson, first of all, we shall explain the exact meaning of graph sketching and how it is done. And then we shall talk about the inadequacy of commercial packages. There are so many commercial packages that can help you to draw graphs. But as a matter of fact, the strange thing is that you will find that when you do it yourself, it's much better than you use commercial packages. Because commercial packages give you a whole picture, whereas you are looking specifically for the specific properties that you are of the graphs, and this is done better by you. Now, and what are also, we speak of the graphical properties of functions. Now, what's the meaning of graph sketching? Now, the graph sketching, as a matter of fact, is to draw the curve of the function. In other words, to take particular values of x and to draw the graph or the curve y is equal to f of x. But you don't need to do a table and then give values over x or calculate the value of y. You don't need to do that. You can do it as a whole, but because you are sketching the function, we are not drawing it exactly. We want to imagine or to have an idea about the main properties of the graph. So, in other words, by graphing or by sketching, you mean to track the behavior of f of x when x change value in a given interval. You are interested, if you are interested on the whole region, on the set of real variables, on the set R, then you may study the whole interval from minus infinity to infinity, but you may wish to assign yourself to a certain period or a certain interval, and you wish to locate the main properties of the graph in that particular interval. Now, practically how this is done. Usually you assign values to x, which is the independent variable, in the domain of the function, and then you record the corresponding values of f of x. You don't exactly do that, but this is how, this is the meaning of to graph a function. Now, here is the coordinates of Descartes, who is the philosopher, a French philosopher in the 17th century, who has been able to transform the geometry of Euclid of Alexandria into what is called analytical geometry. He chose two coordinates, orthogonal coordinates, or two axes, x and y, and then any point P is an ordered pair of x and y. And when you are given the value, assign the value x, which is the independent variable in f of x, you can calculate the value of y, so you can locate the y coordinate. And if you connect these points together, you get almost the whole graph of your function. Now, when you do this, it means that you enumerate all order pairs. You have for each x, xi, because this is a function, so for each x there exists only one y in the range of the function. So you enumerate all order pairs, x, y, and yi from 1 to n. In other words, you consider taking n points to represent your graph. And then locate all those points on the x, y plane. And after that, you connect all these points together to obtain your graph. So finally, you connect the points. When you connect them by what? By straight lines, of course. You don't connect them by a simple curve, just straight lines. Of course, the more you take as points, the more you don't seem to look. They don't seem to look like connected straight lines because the curve turns over, etc. So the graph is represented by points, and those points you connect them together so they don't look exactly like their corrugated ones, but they're smooth. The graph goes smoothly the more points you assign. So by assigning more points to the independent variable x, of course, the representation of your graph is improved. For example, you have here a simple parabola, y is equal to x squared, and you wish to draw the graph of the function between 0 and 3. So for example, let us say we start by 7 points. So you assign 7 values for x, and you calculate the opposite value of y. This is 0.5, you square it, you got 0.25, 1 corresponds to y, etc. You calculate yi from x squared to all these points, and then you connect them together and you obtain such a graph. Here you find them, you connect them by straight lines, so you find that the representation is not very good. Why? Because the points are dispersed. So the more points you take, of course, the graph looks more smooth. Here, the graph, you're taking n equal to 13, so you notice that the accuracy improves better. Now, what is we said there is an inadequacy of commercial packages. The commercial packages are not really better than you when it comes to graphing functions. Of course, it's much easier for you to do it, but it's not that what is meant by sketching the graph. What is meant is that you want to get acquainted with the properties you are searching for of the graph. It's not a matter of seeing a graph, but it's a matter of saying, for example, at this particular point there is an inflection point, and at that particular point there is a turning point, or there is a stationary point, etc. So there is some kind of inadequacy, in fact, using commercial packages, because commercial packages, what I meant by commercial packages, the one in the market, they help you in drawing graphs of functions. They can tackle, of course, the problem with efficiency, as a matter of fact. But all we need all they need, as a matter of fact, these commercial packages, you give them y is equal to f of x, it's done automatically, mechanically. And they plot the graph. But you tell them, for example, I want the scale to be so and so. So you give them what's meant by the aspect ratio. In other words, for example, if you draw a rectangle, for example, or a square even, you tell them, for example, I want the height to the base, or the scale of the height, for example, or the y-axis to be, for example, from 1 to 10. This is called aspect ratio. Sometimes it's oval, but how much is it oval? For example, is the radial, for example, the height or the vertical diameter, for example, how much relatively it should look with respect to, for example, to the horizontal diameter, etc. So these are called aspect ratio of your graph or of your figure. So you give them the aspect ratio, the shape, whether you want it to be continuous or whether you want it to be dashed, for example. You want it to be intermittent, in other words, not very much continuous. They're composed of dots, etc. And then the software does the rest for you. But still, this is not so. Why? Because there are some graph characteristics, as I said, that cannot be reached by commercial packages. For instance, let us take a very simple example. This is, for example, you have here y is equal to x divided by x squared minus 3 to the power square, and you choose, for example, 11 points. Why? It doesn't matter the number of points you take, because for every graph you can find, for example, a set of points at which beyond this the graph is well, and below this the graph is not good. So for this particular graph, for example, we take n is equal 12. So when you take n is equal 12 and you try to locate the value of y, and then you connect them by straight lines, you end up with something like this. These are 11 points that you take to consider the graph of the function that we have just mentioned in the last slide. So you have something like this. Is this the exact graph of your function? In fact, no, this is the exact graph. Because you say, perhaps you think because we took n is equal to 11 only, had we increased the number of points, yes, but we could have found other graphs that even if you take much number of points, that you may be, you find an inadequacy in representing your graph. So whether as here in the slide before this one, the graph was very it wasn't really a good representation of your function. This is the exact one, and they are really far from each other. So you see now why is it better always for yourself to investigate it yourself and to try to sketch the graph, and we shall see how we do this. So commercial packages, in fact, for drawing graphs are not capable of first tabulating all the points. Only they take a choice or a simple number or some chosen points only from all the points that you can take out of the domain of the function. Again, they cannot clarify the behavior between the chosen points because you connect them by straight lines. So in fact, they neither tabulate all the points, and then they connect them by straight lines, so they may look completely strange from the exact sketch or from the exact shape of the graph. And then scanning the whole domain is difficult for them. They usually you assign for them, you prescribe the domain for them. You tell them, for example, try to calculate, for example, f of x, or to draw the graph in a certain interval. But when you do it yourself, then you can scan the whole domain of the function. In other words, your method is valid for the whole of the set R. So this, of course, would be much better. Before we consider how we sketch a graph, we have first to study the graphical properties, and we spoke about them when we, in fact, when we were studying you remember in one of the lessons, the early lessons about the classification of functions, and you said it could be explicit, implicit, the parity could be even, could be odd, it could be attenuated, it could be monotonically increasing, decreasing, it could be periodic, etc. So these are called graphical properties of functions. So the graphical properties of functions are many of them. First of all, the symmetry. For example, if you know that your function is even, then there is no need to draw the function in all the xy plane. You may restrict yourself, for example, to the values at which x is positive, and then the other one is complete duplication of it, because you know that the graph, your graph repeats itself on the left-hand side when you put a mirror. In other words, the parity of the function is even, and whether it is odd, in other words, is symmetric about the origin. So one piece of the graph is enough in order to repeat itself in the other opposite plane. So now the function is even if f of minus x is equal to f of x, whereas it is odd if f of minus x is equal to minus f of x. Again, the monotonicity. For example, the curve is ascending if f dash of x is greater than 0 for all x element of the domain of f, and it's descending if f dash is less than 0. So if the function is increasing, f dash is positive, then we call it ascends, whereas f dash is negative, we call the function is descends. Now again, the intersecting with the axis, and this is important because it gives you the clues, like the corner points. Is like, for example, you have locating, for example, a shop. You say it's near the metro, for example. So when you search, you search for the metro, then you know that the shop is nearby. Then you reach first for the metro station, and then you look around to see whether your shop, the one that you want to go to, exists. Same thing here. You can locate points at which the function, because the function passes from below the x-axis to the upper part of the x-axis when y naught is 0. Because so these are the roots of the function. The intersection with the x-axis is when f of c is equal to 0. In other words, y is equal to 0. So the curve, your curve here, if you have, for example, a function here, now, and it passed like this. So this point is the point at which x is 0. So this is y naught. This is f of naught. Whereas here, this is the point C at which f of c is equal to 0. So if you have, for example, something like this, x minus 2 divided by x plus 3, this is equal to what? This is, make it positive to make this positive. So at x equals 0, this value becomes equal to 2 over 3. Whereas here, this point will be equal to minus 2 because this is the value at which f of x equals 0. So there, this point is important because you cannot pass from this region to this region except you pass by this point. And same thing here, you cannot pass from below the x-axis to the upper part of the x-axis unless you pass by this point. So these are clues that you can that can tell you where to go or where to pass from a region to another. Again, if the function is continuous, it's easy, of course, because there are no intermittent or jump, because we investigated this before, and we spoke about the type of discontinuities that you have. If the function is continuous, then you need not worry, and you just you can connect the graph together, and you need not worry about whether there are parts or places where the function is discontinuous. Again, you can have asymptotes, and these are very helpful ways of drawing functions, because if you have an asymptote, for example, a vertical asymptote. What's the meaning of vertical asymptote? A vertical asymptote is a line to which the functions runs parallel to it till infinity. And how would you locate it easily? You get the roots of the denominator. And for example, for this particular function here, you have here directly you have an asymptote x is equal to minus 3. How did we know this? Because you locate the zeros of denominator, or the roots of the denominator, which is x is equal to minus 3, at which the numerator is not 0. So the numerator at x is equal to minus 3 is equal to minus 1 is not 0, and therefore x is equal to minus 3 is one asymptote of the function. So this for the vertical asymptote. Whereas for the horizontal asymptote, it's easy. You take the limit when x tends to infinity. Like for example, this one, the same example here, x plus 2 divided by x plus 3. When you take the limit when x tends to infinity or minus infinity, you get 1. Because we said before, you divide by the highest degree of x. So this was transformed to 1 plus 2 over x divided by 1 plus 3 over x. So when you take the limit when x tends to infinity, this cancels out, this cancels, and you get 1, meaning that the curve is parallel to the line y is equal to 1. So you have vertical asymptotes, which are, you obtain them from the roots of the denominator, and you have as well horizontal asymptotes. You obtain them when you take the limit when x tends to infinity. So, and these help you in locating or shaping the graph, how the graph would look like. And then you have critical points, the one that we just spoke about in our last lecture. We spoke about maximum and minimum. If you can locate critical points, that helps you very much, because these are the points at which the function attains its maximum or minimum value, especially the local points, because global extrema, since you are working on the whole real line, so what are the importance really? The local extrema and not the global extrema. Because the global extrema here, they don't really constitute any importance, because there will be 1, because here the interval is open from minus infinity to infinity. So what are the importance are the local extrema, and because you want to draw the graph. You don't want to evaluate the extrema. You just want to see how the graph turns from, for example, from a local maximum, and then after it climbs up, how it goes down again. So it's local extrema which are important, and these are determined through the critical points. Again, you can, of course, check also the region of convexity and concavity and the inflection points. And of course, these depend, as is said here, the sign of the second derivative. And with this, we have explained them in detail in our last lectures. And then this is here. There is a graph of a function. Which is, you don't have necessarily to take this one, but you may take another one. Let us take one to see if it is easy or not. Let's take any one randomly, for example, x plus 2 divided by x minus 3. And you want to draw them. You directly take any orthogonal axes, and here at x equals 0, you get minus 2 over 3. And then y equals 0 at x is equal to minus 2, so it passed by this point, and by this point, and it has an asymptote x is equal to 3, and it has an horizontal asymptote y is equal to 1. So how do you think the curve would look like? I myself will take it directly like this. You don't have to think too much. And this applies to any other graph. So here, x minus 2 divided by x plus 5, what you have here at x equals 0, you get minus 2 over 5, it should pass by this point. And then it has, at 2, you have y is equal to 0, so it must pass by this point. And there is an asymptote, horizontal asymptote here, and the vertical asymptote at minus 5, so it must look like this. This is another one here. X divided by x squared minus 1. How would you draw it? It's easy again. Now here, at x is equal to 0, y is equal to 0, so it must pass by this only point from below to the upper region of x. Again, it has two asymptotes. How do you obtain them? You take the roots of denominator, which x squared minus 1 equals 0, so you get at 1 and minus 1. Again, when you take the limit when x tends to infinity, you get 0. So the horizontal asymptote is y is equal to 0. The vertical asymptote is x is equal to 1 and y is equal to 1. The function also is an odd function. So it's enough that you draw it on the right-hand side of y, and the other one would look like it. So here, it must go this way, because when x is greater than 1, this is positive. And when x is less than 1, this is negative, yet this is positive. So it goes like this. And since it's odd, it must be inverted like this. And this is a point of an inflection point. And you can easily calculate it by evaluating the second derivative. If you evaluate the second derivative, you find that the second derivative is 0 here. If you evaluate the second derivative also, you will find that y double dash here is positive, here it's negative, here it's positive, and here it's negative. So there are steps which you do. You start first by the parity, then the asymptotes, then they intersect with the axes. Here there is only one. So whether you have the asymptotes horizontal or vertical, and then you are looking for the critical points, the maximum, local maximum or minima, and finally with convexity and this and like this, you can directly draw your graph. For example, this is here. You want to draw the graph of this function, x plus 1 times x, we better write it. You have here y is equal to x plus 1 times x minus 2 divided by x plus 4 times x minus 3. And you want to draw it. Now, directly without going into detail. Now you see directly here that the curve passes by the point minus 1 and 0 and 2 and 0. In other words, at when y equals 0, x must be equal to minus 1 and 2. In other words, if we go here and you try to draw it like this, it must pass by the point minus 1, it passes by this point, minus 1, and by the point 2, it must pass by this point. If it has to pass from below, from the lower part of x to the upper part. Again, what are the asymptotes? At x is equal to 3, so this is an asymptote. And at x equal to minus 4, and this is another asymptote. All right, is there any horizontal asymptote? Indeed, when you take the limit when x tends to infinity, you got y is equal to 1, so this is a horizontal asymptote. All right, so what about at x equal to 0? At x equal to 0 is equal to minus 3 over minus 12, is equal to 1 over 6, so it passes by these points. So it passes by the point 1 over 6 here, 0 and 1 over 6, minus 1 and 0, and 2 and 0. It has a vertical asymptote at x is equal to 3, and another one at x is equal to minus 4, and a horizontal asymptote y is equal to 1. How you draw this graph? What do you think it would look like? I myself would take it like this directly, without even going further, like this, and it must pass by this point and going like this, and it must be like this, something of this sort. The only thing which matters now is to locate the maximum minimum. Whether this is the maximum, no, there could be a point here which is the maximum. And there could be, as a matter of fact, one point here to be minimum. Or there may be points of inflection somewhere. This need to be investigated further. But what you already, from the graph directly, you can tell what kind of graph it will look like. So first of all, and the problem tells you, study the symmetry, intervals of increase. Of course, here there is no symmetry. The parity, there is no parity, even or odd. The interval of decrease and increase. How would you calculate the interval of increase or decrease? From the derivative. And the intersection with the axis, continuity, asymptotes, of course, in the problems. You wish to study all this, because these all are properties of your function. But as graph, you can directly get to the paper and draw your graph. Here, First of all, the graph is unsymmetric with respect to the axes, because if you put x is equal to minus x, you get something altogether different, and therefore here it's neither even nor odd. Again, from the derivative, this is the derivative. You directly see here the derivative that what are the critical points? The critical point is 3 is the critical point? Of course not, because 3 does not lie in the domain of the function. If you look here, 3, x minus 3, you divide by it. So 3 here, neither 3 nor minus 4 lie in the domain of the function, and therefore here from y dash, 3 and minus 4 are not the critical points. So what are the critical points? The critical points are the points 9.243 and 0.757. So there are 2 critical points, and these 2 are interior points to the domain of the function. Now directly I can anticipate that you have 2 extrema, local extrema. So perhaps these 2 extremas are the following: one here and somewhere either here or there. And the curve turns again. If there is one here, so sure the curve must go again to be parallel to the line y is equal to 1. So sure there must be an inflection point somewhere, either here or there. We don't know yet. So we investigate it further. Here are the intervals. I took the intervals of the function from minus infinity to minus 4, which is the first asymptote. Then from minus 4 till 0.76, which is the point, the first critical point. And then from the critical point to the other asymptote. And then from the asymptote to the other critical point until infinity. So you scan the whole domain from minus infinity to infinity. You see directly here that the curves here ascends in the first interval and ascends 2 in the second interval. And here you find it on the graph here. You see here, y dash is positive here. And again, it's positive here. In other words, it's ascending here and ascending here. And then again, it descends after the point 0.76, which means what? Which means that the point 0.76 here, it's a local maximum, because the graph y dash is positive here and negative here. So it climbs up and then go down. So this is a point of local maximum. Whereas from the graph here, you see here what? You see that the point in the it goes down in the last before last 2 intervals. It means that the function here it goes down here like this, it descends, and here also it descends here. But then it goes up again at 9.2 in the other interval. After 9.2, the derivative is positive. So the derivative is negative here, and positive here. So it means that the point 9.2 is a local minima. So now you know that there are 2 local extrema. One is local maxima here and one is local minimum here. This is an achievement, of course. So there remains to know if this is a local minima. So I'm expecting that the curve, since it turns down, because look here, if you zoom on this part here and you magnify it here, here is the x-axis and here is your line. It comes like this, so it must turn over because this is the asymptote. So sure, there must be a place here where the curve was having a convexity downwards, convexity downwards here, and then again here it is, I'm sorry, a convexity upwards and then a convexity downwards. In other words, y double dash must be here positive and here negative. So there must be somewhere a point of inflection somewhere on the graph. So here it is. The curve cuts the y-axis at 1/6. This we found it before. And the intersection with the axes, the points -1 and 2. These are the points at which it passes from below to the upper side of the x-axis. These we already located them. The function is a rational function, and therefore it's continuous everywhere except at the roots of the denominator, which are at which the asymptote exists. So this we found already. So the curve has a vertical asymptote because you take the limit when x tends to -4 from the left-hand side, or from the right-hand side you go to infinity or minus infinity. And this we have located them before, because you do not have actually to take this is an academic kind of exercise. You take the limit, but you can directly locate it from the rational function, because you locate the roots of the denominator and you set them 0, and these are your asymptote directly. Here x is equal to -4 and x equal to 3, and at the same time you take the limit when f of x, when x tends to infinity, is equal to 1, so you locate your horizontal asymptote. And finally you have now the critical points. The critical points, we already found them, because they are the points at which y dash is equal to 0. They were 2, and they evaluated the maximum. We found them to be equal to, at the point 9.24, 0.89. So this is less than 1, which means that your local minima is less than it's is below your horizontal asymptote, whereas the local maxima also is below your local your horizontal asymptote is equal to 2. This is a local maxima and this is a local minima. And finally, I expect that here is your graph, but there remain one point. Here, look at this. This is your vertical asymptote, I-4, and this is another one at 3, your vertical asymptote, whereas you have one horizontal asymptote, y is equal to 1. This is your local minima, and this is your local maxima. And here, since the curve here tends to converge to y is equal to 1, which is your horizontal asymptote, so sure there must be a point here at which there is an inflection point. So what you do is that you can obtain the second derivative and construct again your table of second derivative from plus to minus. You get concave the points when you have f double dash changing in a region plus to another region negative. It means that the curve here you have here a concavity. Here you have a concavity upwards, and here you have a concavity downwards, etc. I call them concave and convex, doesn't matter. And you have one inflection point, and you see here there is really one inflection point at a point having a y coordinate less than your horizontal asymptotes. Again, this is another graph, y is equal to mod x over x minus 1. Again here, if you want to study it, the curve is unsymmetric again with respect to the axes. And this is your derivative. How do you take the derivative of this? The derivative of mod x, we said before, is equal to mod x over x. So here, when you want to obtain the derivative of this function, you obtain mod x over x with the derivative of the numerator times x minus 1 minus the numerator times derivative of the denominator divided by the denominator square, and you get an expression like this. Directly, when you see this here, what are the critical points? Directly, the point x is equal to 0. This is the critical point. Here, the function is, as you see here, x is equal to 1 is not critical point. Why? Because it's not an interior point. It does not lie in the domain of the function. So you have one critical point at the point x equal to 0. That's all. And of course, at x equal to 1, it does not lie in the domain of the function. So here, you try to locate the interval. Here, the interval, you try to locate the sign of your function, f dash. Here you find it positive, then negative, meaning what? This is the critical point, the point equal to 0. A critical point, of course, 1 is not a critical point because it does not lie in the domain of your function. So here, the f dash changes sign from positive to negative, meaning what? Meaning that it's a point of local maxima. So you have a local maxima, one local maxima at the point x equal to 0. The curve also passed by the origin, because at x equal to 0, here we have the function directly. Your function is mod x divided by x minus 1. So sure, here there is a point of local maxima. The curve passes by this point. It has an asymptote x equal to 1. It has also an horizontal asymptote. If you take the limit when x tends to infinity, you get what? This is positive and this is positive, so you had one horizontal asymptote, y is equal to 1. But when this is negative, you get minus 1, so you have when x tends to minus infinity, you get y is equal to minus 1. So how would you draw such function? It's not difficult, of course. The curve passes by the origin, as I said, passes by this point here in the middle. So what you have here, the function is continuous, of course, except x equal to 1, which lies in the denominator of the function. And then the curve has a vertical asymptote. Of course, here is your, on the graph here, here's your vertical asymptote. Here, when you locate the function here, it must go like this because the derivative is positive somewhere here, and then it is negative here. So I assume that it must look something like this, whereas here, when x is greater than 1, this is positive, so it must be something like this. There must be also, I assume this must be the situation. I don't think there is more than this, but we shall see anyway. So here you have two horizontal asymptotes, as we have described now on your graph. You have one vertical asymptote, x is equal to 1, exactly, where the function reaches infinity from the right-hand side and minus infinity from the left-hand side, and this is right on our graph, and you have two horizontal asymptotes. And the point x equal to 0, exactly, this is the only critical point, because 1 does not lie in the domain of the function, whereas 0 is an interior point at which f dash does not exist, so it's good. So what else do we have, really? Here it is, and this is exactly coincide. I don't remember it exactly, but it must be looking like this. What remain, I assume we must study the convexity and the concavity because we don't know really how the curve would look like. So what we do, what remains really is to study f double dash. It's not difficult. If you go back to our curve again, let's make it a little bit more. You have here mod x divided by x minus 1. So here, first of all, at x equals 0, y equals 0, so it must pass by this point. At x equal to 1, when the denominator is 0, you get x equal to 1, so this must be your vertical asymptote. Of course, you can say that the limit when x tends to 1 from the right-hand side is infinity and from the left-hand side is minus infinity. In other words, it goes like this and like that. It's up to you to say it. But it has two horizontal asymptotes. Why? How would you calculate them? You take the limit of mod x over x like this. 1 minus 1 over x. So when x tends to infinity, this cancels out, and you get limit mod x over x. The limit of mod x over x depends on the sign of x. If x is positive, this is equal to 1. If x is negative, it's equal to minus 1. So surely there must be two horizontal asymptotes like this. From the right-hand side, it approaches 1, and from the left-hand side, it approaches minus 1. And it passed by this point. How do you think such curve would look like? How do you think? If from the right-hand side, it goes to infinity. In other words, from on the right-hand side of 1, it must go to infinity. It must go this way. And then it must saturate to y is equal to 1. So it should look like this. From the left-hand side, if x is less than 1, this is negative. So sure, it goes this way. But it must pass by this way, by this point here, 0. And then also it must saturate to y is equal to minus 1. So sure, it must go again like this. Especially that here, when you calculated the derivative, you found equal to modulus x over x. In other words, the derivative does not exist at the point x equals 0. So although this is an interior point and it's a critical point in the domain of the function, at which this is a turning point, is not a stationary point, because f dash does not exist here. So it means this is a local maxima, the only local maxima. And what remains then only is to see whether the curve, this helps you again, whether the curve is concave or convex, in other words, concave upwards or downwards in these areas. I assume that if you obtain the second derivative, you will find that this is positive, and here it's negative, and here is positive. Anyway, we have to check this on the graph. So we calculate from the second derivative. Here is again, and we here, when x is greater than 1, this is positive. Like we said here. Here, like you see here, the y double dash is positive. So it's concave upwards. Whereas when x is less than 1, this is negative. And this is positive, so it's negative. So this is concave downwards, like you see here. And again, when x is negative, this is what? This is negative. And again, this is negative, so it's positive. And of course, this would be on this part here, the function, the graph would be concave upwards. So in fact, we drew it already correctly. So with this here, we can check, as I said, the concavity upwards and downwards from the sign of f double dash. Here it is concave upwards, here is downward, as here is upwards. And what is interesting here is the point 0 is an inflection point. Why is an inflection point? Because an inflection point is a point at which f double dash either it's 0 or doesn't exist. So the point which is 0 here, which is something very interesting, it's a point of local maximum, at the same time it's a point of inflection. Because before this, the curve was concave upwards, and after it, it will concave downwards, and it's a point at which f double dash does not exist. Therefore, it's a point of inflection, and at the same time, f dash here is negative, and f dash here is positive, so it's local maximum. So again, this is a point of local maximum and a point of inflection, so it's very interesting to see this. With this, we've come up to the end of this interesting lecture, and it's not frightening at all to sketch the graphs of your functions. It needs a little bit of patience, and you follow a set of finite steps. It doesn't come from void. You have to follow the steps, and once you follow the steps one by one, you will be able to sketch your graph very easily. So at the end of this lecture, I thank you for your attention, and I keep always, like all the time, reminding you that all these lectures, and this one, of course, the one that will come after all of them, are uploaded to the site of the Unituno Telematic University. And until we meet again, I thank you for your attention, and I'm wishing you a very good luck. Thank you.